Hello and welcome back to the Texas Financial Derivatives YouTube channel. Today we're going to discuss kind of a general introduction to binomial trees, and we're going to talk about how they're used to price European calls and puts on stocks. So let's jump right in here. Suppose we have at time zero some initial stock price S0, and then we want to kind of look at the movement of this stock over some time period H. So the easiest thing to do is to say, well, the stock can go up or the stock can go down. And we'll get a little bit better line going there. So what we denote the up price and the down price as is just SU or SD. And an easy way to think about these two prices is that they're just the initial stock price times times some up factor, or the initial stock price times some down factor. So let's say that we're looking over this time interval H, and we say that the stock, based on whatever model that we've run, can either go up 10% or down 15%. Then U would have to equal 1.1, and D would have to equal 0.85, and that makes sense, right? The stock's either going to go up to 110% of its original value, or it's going to go down to 85% of its original value. And so one kind of important thing to think about is, where does the forward rate fit in with all this, right? So if you remember, the forward rate over some time interval 0 to H for some stock S is defined as, the forward price is defined as the stock price at time 0 multiplied by e to the r minus delta times H. R, remember, is our continuously compounded risk-free interest rate, and delta, remember, is our continuously compounded dividend rate. And so for a continuously compounded dividend paying stock, or a stock paying continuous dividends is a better way to say that, the forward price on that stock over some time period H is going to be the value of that stock today, accumulated for interest, and then kind of discounted for the dividends that would otherwise be received if you were holding that stock over that time period. And so this is just, remember, the forward contract is just between a buyer and a seller. It's a contract to purchase. So here's time 0, here's time H. So no money's originally exchanged here. You just have the contract is signed, and then it's a contract to facilitate purchase of the stock or of the asset at time H. So at this time period H, the asset is exchanged for forward price, F sub 0, comma H S. And so that forward price, because we're waiting until time H to purchase that stock, the forward price is defined sort of in this way, accumulating for the risk-free rate, but discounting for the dividends that would have otherwise been received through this whole time period H, where the buyer is having to wait to obtain the stock. So that's the fair forward price. So the question that's kind of pertinent here is, well, how does this forward rate fit in, or in other words, the price that we would be willing to pay at time H for the stock that's decided upon today. And the answer is, well, to prevent arbitrage based on a forward contract, we actually have to have this kind of inequality satisfied. And the reason for this inequality is that if any other arrangement of these variables were true, for example, if e to the r minus delta H, or the forward rate accumulation factor, were less than the rate of return, and you can think of U and D as kind of rates of return, right? So in our example up here, the rate of return can either be 10% or negative 15%. So if the accumulation factor over time length H for the forward rate is always less than any accumulation factor for the stock over time period H, then it's wise or profitable always to invest in the stock and short the forward, right? And you make money that way. Or if it's always the case that the forward rate of return is less than the projected rate of return on the stock in every scenario, then you would just short the stock and long the forward, and in both of these cases you would have a risk-free profit because you would be completely neutral in position. You'd be long in the forward and short in the asset, and so you'd be totally neutral in position, or short in the forward, long in the asset, one way or the other. So you'd be completely kind of immune to any kind of change or any kind of volatility, I guess, or any kind of movement in the stock. You wouldn't care which way it's going. You're going to make money regardless because you know that this thing is true. So to prevent arbitrage, we make it the case in these models that this inequality is true. So stemming from that inequality, what happens? Think about what happens if we multiply through by the price at time zero, right? So now that we know, we're convinced that this is true, what happens if we multiply through by the stock price at time zero? Well, we see that the fair value of the stock today for purchase at time H is between the value if the stock goes down and the value if the stock goes up. So what does that tell us? Well, it tells us that there is a weight that can be applied to the value of the stock if it goes up and the value of the stock if it goes down, so that the forward price of the stock for today for purchase at time H is equal to the weighted average of the value of the stock if it goes up and the value of the stock if it goes down. So it tells us that the value of the stock, if it were purchased at time H, agreed upon today, has to be equal to some weight applied to the value of the stock if it goes up, plus the complement of that weight, 1 minus that weight, times the value of the stock if it goes down. So the next question is, well, what's this weight? How do we define that? And so we can solve for a formula for this weight, algebraically pretty easily. So let's cancel out this common term here first, and let's say e to the r minus delta h, the accumulation factor for the forward, is equal to u times the up factor times the weight plus the complement of the weight times the down factor. Let's isolate this weight term. So the accumulation factor for the forward is equal to the up factor times the weight plus the down factor minus the down factor times the weight. Let's bring that down factor over to the other side. So the accumulation factor for the forward minus the down factor is equal to the up factor minus the down factor, factoring out the W, right? And that's not a very good W. There we go. And so then finally, the weight is equal to the accumulation factor for the forward minus the down factor, all divided by the up factor minus the down factor, and that's equal to the weight. So typically, this weight is denoted as P star, and the reason that it's denoted P star is because the star indicates a risk-neutral pricing scheme, and then P is going to talk about P is in reference to the fact that it's commonly interpreted as a probability, because we have the case that P star has to be less than 1, less than or equal to 1, and greater than or equal to 0. It's commonly interpreted as a probability, right? Because remember, this is the boundary condition for a probability, right? So it's commonly interpreted as P star is the risk neutral probability of price increase. So based on our up and down factors out of our model and based on the observed risk-free rate and the observed dividend rate, we have some risk-neutral probability of the stock going up. So we can kind of go back to that weighted average, and we can say, well, then the price today must be the price or the forward price today, let's start with that, must be the weighted average P star of the value if the price goes up plus 1 minus P star times the value if the price goes down. And so then S0, the stock price today, has to be the that weighted average discounted at the forward rate. So discounted at R minus delta over time period H. So why is this important? You may say, well, Austin, you're going in circles, right? Because this was the kind of the formula for the weighted average that we defined above. This is important because what we can do is define payoffs for an option. Let's define V0 as the payoff or the value. Value is a much better word for that. So let's say this is the value of option today, of an option on this stock. Let's say VU is the payoff at time H of option if price increases. And then VD, let's define as, similarly, the payoff at H, time H, of our option if the price decreases. Great. So we have V0, the value today, VU, the value if the price increases at time H, or the payoff of the option if the stock price increases, and then VD defined as the payoff at time H of the option if the stock price decreases. So now we can define V0 as the weighted average of those payoffs. We can replace that stock price with the value of our option. And this is how we can price e to the negative r minus delta h. This is how we can price our options. And the sort of a pretty good assumption to make is that options don't pay dividends. Sometimes they do, and that's what Merton added to the Black-Scholes model, right? That's why it's called the Black-Scholes-Merton model, is because Merton came in and did some work on options which pay dividends. But it's a pretty safe assumption, and it's going to be kind of our assumption that the dividend rate is 0 for all of our options. So then the value at time 0 of the option is the weighted average of the value if the stock price goes up plus the complement of that weight times the value if that stock price goes down, all discounted at the risk-free rate. We'll put the rate out in front. Risk-free rate over time length h. So that's why that sort of weighted average formula is important, right? So that's a pretty decent way to risk neutrally price an option, and this is known as the expected present value of our option at time 0, right? Of the option whose expiry is H and who has payoffs VU and VD, right? So let's think about a call, right? Let's suppose we have an at-the-money call with strike price K is equal to so that means the strike price is equal to the price of the stock today. So then the payoff is given by the max of the stock price at time H minus the strike price and 0, which is the same as the max, because we have an at-the-money call, it's the max of the stock price H minus the stock price today and 0. So let's look at the tree for this, right? So it can either go up or it can go down, right? So here's the value of the option today, right? And here's the payoffs of the option at the up node. VU is going to be equal to the maximum of, at the up node, it's the maximum of SU minus S0 and 0. And then VD is the maximum of SD minus S0, the price of the stock if it goes down minus the value of the stock today, and 0 versus the price of the stock if it goes up, and minus the value of the stock today, and 0 is the payoff at the up node, is in the payoff at the up node. So yeah, that's what I'm getting at here, is that the payoff at the up node, this part here is positive, right? So that's our positive payoff. We have a positive payoff here, and then this is going to be negative by those inequalities. And so that just comes from the inequality that we defined above, right? About D having to be less than the forward accumulation factor and having to be less than U. So therefore D is less than U, and so D is going to be the down movement, and U is going to be the up movement. And the idea is that U is greater than the value of the stock today, and D is less than less than 1. SU is greater than the value of the stock today. SD is less than the value of the stock today. So this part, based on those inequalities, is negative. So our payoff here is just 0. So now how do we define the value of the option today? Well, we just use our formula that we defined up here, our weighted average formula. And we're going to say that that's just going to be P star times SU minus S0, stock if it goes up, stock price if it goes up, minus the stock price today, plus 1 minus P star times the payoff at the down node, which is 0, all discounted at the risk-free rate, right? And so then that's just going to be P star, the probability of the up movement times the value at the of the option if it moves up. This is going to go to 0, and so then we're still going to have to discount. So e to the negative RH. So that's the value of our call, right? And so kind of in general, you could maybe for a call expiring at time H with strike price K, you could say that it's the value of the stock minus the value of the strike at the up node, discounted back, and that's of course assuming that that K is in between the value of the stock if it goes up and the value of the stock if it goes down. But you can kind of play around with the formula, play around with some numbers, plug in some values that are, somewhat reasonable, and kind of try out pricing different options that way. One useful extension that you can make of this model is to have multiple periods, so a multi-period tree. And so that's going to look like, you have your stock price at time 0 again, and then you go out one period, which is what we just discussed. So this is from 0 to H, and then you've got another period in there, and it's going to go from H out to H, right? So this is SU, the value of the stock if it goes up. This is SD, the value of the stock if it goes down. This up here is SUU, the value of the stock if it goes up twice. This is SUD, the value of the stock if it goes up and then goes down. This is SDU, the value of the stock if it goes down and then up. And then this is SDD, the value of the stock if it goes down twice. Something that you might notice is the equality between these two, and that's because of the multiplicative constants U and D. So this is S0 times U times D. This is S0 times D times U. There's a law about multiplication there that says that these two things are equal, so these two things have to be equal. And then you have up here similarly defined as the stock price if it goes up is up twice is the stock price initially times the up factor twice, and then the stock price if it goes down twice is the stock price initially times the down factor times the down factor. And we can sort of similarly define payoffs, right? If we just look at the probabilities of ending up in any of these states, right? And so this state is kind of the same state, or these two states are kind of the same. So the probability of reaching this state is the same as the probability of reaching this state because they're the same state, right? So that makes sense. So the probability that you're going to go down, that the stock price is going to go down twice is, well, you have 1 minus P star that you go down once, and then 1 minus P star again that you go down again. And so if we assume independence, then the probability for reaching this down node is going to be 1 minus p star times 1 minus p star, 1 minus p star squared. Similarly, the value if you end up at that the up node is going to be p star to get to the up node multiplied by p star to get to the up node to get to the second up node. So the probability of making it to this up node is p star squared, and then the probability of going up and then going down is going to be similarly defined. It's p star. There's a probability p star that you move up, and then a probability 1 minus p star that you move down. So that's going to be p star times 1 minus p star. And then similarly defined is the probability of going down and then up is you have to go down in the first step. So that's going to be 1 minus p star. There's a probability of going down, and then it's going to be p star is the probability of going up here. So then this probability is 1 minus p star multiplied by p star. So again, these two are the same state. So it makes sense that the probabilities of reaching them are the same. The probabilities of reaching the up-down state is the same as the probability of reaching the up or the down-up state. So to kind of analog back to that one period model, we can similarly define a weighted average for S0, right? So in this case S0 is going to be equal to the probability. It's the weighted average of the probability of being in this state, in these two states, which is the same, and in this state multiplied by the respective values of the stock in those states, right? So you're going to have p star squared times SUU plus 2 times p star times 1 minus p star times SUD, or equivalently you could write SDU there, plus 1 minus p star squared times SDD, and then of course all that needs to get discounted at the rate on the forward. So that's e to the negative r minus delta times 2h, right? And that's because you're discounting back to time 0 from time 2h. So you're going from here to here. So you have to discount back at 2h minus 0, which is just 2h. So you're discounting back 2 time periods, right? And so that's how you'd value the stock today. And similarly, you can insert the value of an option today is equal to p star squared times the value of the option if the stock goes up twice, plus twice p star times 1 minus p star times the value of the option if the stock goes up and then down, or down and then up equivalently, plus 1 minus p star squared times the value of the option if the stock goes down and then down again, all discounted at e to the negative, all discounted at the risk-free rate. Remember, our dividend rate on our options is 0 for two time periods h. So that's how you could price a European option. Is then you could say, well, this option is going to have a payoff of say you have a call that's got strike price K, expiry 2H, and it's a European call. So at that point, the value at expiry, if you're at the up node, is going to be the max of the value of the stock at the up node minus K and 0. The value at the up-down node is going to be equal to the value at the down-up node is going to be equal to the max of the stock price if it goes up-down. If it goes up and then goes down, minus the strike price and 0. And then the value at the down node is going to be the max of the stock price if it goes down and then goes down again, minus the strike price and 0. So then obviously you could just take the weighted average of those three values based on these probabilities that have been given, and then discount that at the risk-free rate, and you would obtain the expected present value or the fair value of that call today, the risk-neutrally priced value of that call today. And dependent on what you and D are, this may have a positive payoff, or it may have a zero payoff. And this may have a zero payoff. It probably will have a zero payoff, assuming that it's around being at the money, or it's really dependent on the different factors that kind of go into your model. And but depending on what U and D are, any of these may have positive payoffs or zero payoffs, and it's kind of up to the modeler to select U and D. And so, there's kind of the McDonald model that selects U and D based on the volatility and the forward prices. And then there's many other models that are out there that kind of estimate U and D. And so this is kind of just a basic outlay of the binomial asset pricing model. One thing to note why it's called the binomial asset pricing model, right, is because these probabilities are binomial, and so you can kind of tell that these sort of probabilities come from a binomial distribution, right? That you have some probability of success P star, right? And so you can kind of define that as your probability of success, and then you can see that these probabilities are in fact binomial. And so that's why it's sort of called the binomial asset pricing model. And that's sort of a basic introduction to how to think of this model, and how to think of valuing fairly valuing European calls, and then obviously for a European put, you would have sort of the same you would have sort of the same analysis that you would undergo, where you would take these payoffs at all your different nodes and discount them. And so similarly, you'd value a put with the value up being the max of the strike minus the stock price if it goes up twice, and zero. And so you would just flip this you would flip this sort of value around, where it's now the strike price minus the stock price instead of the stock price minus the strike price, as defined in the payoffs of the calls and the puts that we talked about in an earlier video. And then you go all the way down to the value, the down at the down node being the maximum of the strike price minus the stock price at the down node, and zero. And then based on what U and D are, you would have either a positive payoff or zero payoff at these nodes. And so that's sort of a basic outlay of what a binomial asset pricing model is, what it does, and sort of how to obtain the expected present value of European options using it. There's going to be another video that's going to be posted by Matt that's going to walk through how to value American options with early exercise, which is something we'll typically deal with when we're talking about options. And thanks for watching today. I hope you learned something. Be sure to like and follow, subscribe to us on YouTube, and follow us on Instagram. And thanks for watching. Y'all take care. Bye-bye.